In this video, I will talk about the inverse function of a raised to power x. So our idea is to find the inverse function of a raised to power x. Just to remind you, when we had y is equal to natural log of x and its inverse was y is equal to e raised to power x, that we already discussed in our previous videos. Now the interesting case is when we have a raised to power x, how can we find the inverse of this function? Let me just go back and try to understand how the different functions will look like when we change a over here. Suppose when we have a is equal to 1, how the function will look like. Suppose we have 1 raised to power x. The 1 raised to power x is something like this, 1 raised to power x. When we have a is equal to 2, then the function is y is equal to 2x. Okay. Similarly, when we have when a is equal to 3, then the function is 3 raised to power x. And for 3 raised to power x, we have 3 raised to power x. So y is equal to 3 raised to power x. Then we have 10 raised to power x. So this is 10 raised to power x, so on. So that's how the function look like when we change a with 2, a with 1, a is 3, a is 10. Similarly, if a is 1 by 2, for example, a is 1 by 2, then the function is something like this. When we have a is 1 by 2, so we have 1 by 2x, and a is 1 by 3, so a is 1 by 3. 1 by 3 will be look like this, 1 by 3x. So that's how the changing values of a will give you different functions. And remember that the value when a is 2.78, then we get exponential function that will lie somewhere between 2 and 3, somewhere over here. Okay. Okay, now the main question is how we can find the inverse of a raised to power x. Okay, how can we find the inverse function of this value? When a was equal to e, let me just go back and write a is equal to e. So we have y is equal to e raised to power x. Okay, then we have log of e with base e x, which was equal to natural log of x. That's how we did. At that time, I did not write natural log as log of base e. So this was the main idea, to find the inverse of a raised to power x. We take a log, which means we take a log with base a on both sides, log a raised to power x. What is the reason we want to find the x over here? So x will be equal to log of a y, and if you replace x and y together, x becomes y and y becomes x. So we have log of a x. So that's how we define we find the inverse of a raised to power x. Here I have used one property, that log a and a will be equal to 1 over here. Okay, so In neat and clean, we can write y is equal to a raised to power x. Its inverse is y is equal to log ax. When a is equal to 2, for example, 2 raised to power x, then y will be equal to log with base 2 x log 2x. So the inverse of a raised to power x is log with base a x, so on. If you want to see the visualization, a plot of these functions, and we already discussed that these are the reflections against y is equal to x. If we have y is equal to x, this is x, this is y. And if we have, for example, this is 1, and we have y is equal to log of with base 2 x, and its inverse will be that will pass through 1, and we have this y is equal to 2 raised to power x. Okay, so log 2 and 2x are inverses to each other. There are some properties of inverse functions ax and log of a raised to power log of a x will be equal to x. X should be greater than 0. This is the first property, and we already discussed that. Then we can also write log a raised to power x, that is equal to x all x over here. Okay, we can also see that when we have y is equal to log of ax, if we apply natural log on both sides, natural log of both sides, natural log of maybe I should write it first, write this a of y, since first I need to convert that into another formula. We write it like this, log of ax, and by the above property, this property, that is equal to x, and a raised to power y is equal to x. Now I apply natural log on both sides, natural log of a raised to power x, natural log of x over here. And we have y natural log of x, natural log of a is equal to natural log of x. And from here, y will be equal to natural log of x divided by natural log of a. And what was y over here? Y was log of ax. So log of with base a, x will be equal to natural log of x divided by natural log of a. So that's how we find another result. Whenever you see somewhere log with some power of 3, for example, log of 3x, you can simply write this as natural log of x divided by natural log of 3. Similarly, natural log of xy, we already saw that you can simply split that into 2. And similarly, if we have log of a, these are just the properties, product rule. This can also be written as log of ax plus log of ay. And the quotient rule is log of axy, log of ax, log of ay. And the reciprocal rule, I already did this for natural log, so simply I write it quickly. These laws minus log of ay, these remains the same. The power rule, log of a x raised to power y, y log a x. So these are the properties or rules for base A. The only thing which is left in this lecture is to find the derivative of log of A. Derivative of log AX. So the derivative of log with base A will be equal to 1 over, or maybe I can prove it for you. It is, first I just write the answer, 1 over natural log of A, 1 over u du by dx, if we have u over here. The Thomas calculus replacing x with u so that it can also be used for the chain rule as well. So what is the proof? The proof is very simple. We know that log of a u will be equal to d by dx, and this is natural log of u divided by natural log of a, and when we take a common 1 over natural log of x, d by dx, natural log of u, and taking a derivative of natural log of u, this becomes 1 over u du by dx. Since we want to apply the chain rule, so there is u, there is x, so it should be du by dx. And this is the same thing that we already written over here, the derivative, in the derivative form. Okay, so let me just solve one example for you. Example 1. For example, you need a derivative of log with base 10, 3x plus 1. You need this derivative. So it means that this will be equal to, according to this definition, natural log of 10, 1 over natural log of 10. Then we have 1 over, this is u is 3x plus 1, 1 over 3x plus 1. Then we need to apply the chain rule, d by dx, 3x plus 1. And we have on the right hand side 3 natural log of 10, 3x plus 1. This is one example. Now we want to find a integration. So we learn that from the example number 2. We need to find the integration of this function in the integrand. According to the definition, this will be equal to natural log of x, natural log of 2 over x dx. Natural log of 2 is just a constant, 1 over natural log of 2, natural log of x, natural log of x over x dx. Now, let me just substitute some value. Let u is equal to natural log of x, and differential is 1 over x dx. So the above equation becomes 1 over natural log of 2 and u du. That's what we get. 1 over natural log of 2 u square by 2 plus c, and the u will be equal to natural log of x square divided by 2 natural log of 2 plus c. So this is the answer for this integration. This is a very interesting thing over here. So we just finished the section 7.3 over here. This was very interesting section where we learn about the logarithmic function, exponential function, then logarithmic function with base a, logarithmic function with base other than a, which is e, natural log, it is natural log, so on and so forth. Thank you for watching.